All right, so I think we are now live once again. So hello everyone, welcome back to another edition of Quarantine Thermo. Today we're very pleased to welcome Mohammady from RCQI in Bratislava. So Hamed is an expert in sort of quantum thermodynamics, quantum measurements. Today he's going to be telling us about stochastic quantum thermodynamics of projective measurements via coarse-grained trajectories. So before I just hand over to Hamid, I'll do the usual thing of just recapping the basic format. So basically, Hamid's going to speak for as long as he wants once I hand over to him, and then we'll have questions and answers at the end. So if you do have any questions during the talk, as always, please feel free to just write them in the YouTube chat window. And I'll pass them on to Hamid at the end. And please just give your name with your question if it's not already clear from your YouTube username. So I'd say with that all kind of said, let's move on to the science. So I'll hand over to you, Hamid. You can share your screen and take it away.
Okay, thank you very much. So let's get the share the screen. Okay. Right. So can you see the screen now? Just to make sure. Okay. All right. Okay, so let's begin. Yes, so as Mark said, this is a talk on stochastic quantum thermodynamics of projective measurements via coarse-grained trajectories, which is based on an arXiv preprint which came out a few weeks ago. So the talk outline will be as follows. I will initially just give a brief overview of what stochastic quantum thermodynamics is.
Hamid, sorry to interrupt. I just noticed something. So I think there's these little symbols that appear at the bottom of the window. I think to get rid of them, you have to close. There's like a little Skype window with the video that you probably have to close somewhere.
Right. Okay.
So can you try exiting full screen?
Yeah. Okay. I don't see any other windows, but.
Okay.
Yeah.
Well, let me see if maybe it will go away by itself. I mean, this happened previously, and it seemed like.
Yes, I remember.
So. Okay, maybe we can just try it and hope that it goes away.
Okay, sure.
All right. Hopefully, there's nothing at the bottom of the screen that's going to get cut off. That's the only thing.
Yeah.
Okay, I'll let you know if it's
okay.
I'll let you know if it's
my slides are pretty sparse, so hopefully it'll be okay.
Okay. Good.
Okay.
All right. So please carry on. Sorry.
Okay. So right. So again, initially we'll talk about stochastic quantum thermodynamics, which is defined in terms of sequential measurements. So therefore, I will give a brief overview of quantum measurements from the perspective of positive operator measures and instruments. And then I will discuss how we can deal with the thermodynamics of an ideal projective measurement process. And then to analyze the statistics of these thermodynamic properties, namely work, heat, and entropy production, we will use the standard approach of the eigenstate trajectory approach of stochastic quantum thermodynamics, and we will see that this approach fails in certain instances when the quantum system being measured has degeneracies. And to resolve this issue, we introduced a more general trajectory approach, which we call the coarse-grained trajectory approach, which nicely resolves this issue, at least for the case of projective measurements. And then we will illustrate some of the essential features of this phenomenon with a simple example with a two-qubit system. Okay, so let's begin. So consider a dynamical process where an initial quantum state rho is mapped to a final quantum state rho prime by a completely positive trace-preserving map with the Krauss decomposition kx. Now, in classical stochastic thermodynamics, where you have a probability distribution over phase space, which can evolves into another region of phase space, you can decompose that into a probability distribution over trajectories in phase space. So we want to have a analogous setup in the quantum regime. So we want to have, and so we label the trajectories as gamma, and P of gamma is the probability of the trajectory gamma. And these trajectories are operationally conceived of as the outcome of sequential measurements. And of course, there are many ways of doing this, but the most conceptually simple way is the so-called two-point eigenstate trajectories, where gamma is given by the sequence nxn, where n labels the eigenstates of the initial state rho, x the Krauss operator kx, and n the eigenstates of the final state rho prime. And if we then assign a thermodynamic property to each trajectory, namely work, heat, and entropy production, then we can compute all moments by taking the average of the kth power of that property over the trajectories. Okay, so measurements in quantum regime. So there's basically going to be two levels of description for quantum measurements, which we'll need here. One is the positive operator measure description, and the other, the instrument description. So let's first go to positive operator measures. We're going to be dealing exclusively with finite dimensional systems with discrete observables, so everything is fairly simple. So let's say you have an observable with n outcomes, which you denote as a set x with outcomes x1 to xn. And so an observable with these outcomes is the positive operator measure E, which is a collection of positive effect operators associated with each outcome x, such that when you sum them, you get the identity. And then the probability of observing outcome x of the observable E, given an initial state rho, labeled here, is just the trace of the effect multiplied by the state. Now, the positive operator measure description of measurements is fine if all you care about is the statistics of measurement outcomes. But if you want to know how the quantum state transforms due to measurements, and also if you want to then define sequential measurements, you need a more descriptive level of description, which is provided by the instruments framework. Now, every POM E is associated with a class of instruments, IE, which are completely positive trace non-increasing maps, which satisfy the so-called probability reproducibility criterion, which is that the trace of the transformed state by the instrument equals the probability of observing outcome x of the observable E, given the state rho, for all states rho and all outcomes x. Now, since the trace allows us to define a pre-dual of any quantum operation, then we can simply identify the effect with the pre-dual of the instrument acting like the identity, right? Because in this trace, you can put an identity here, take the trace, take the pre-dual of the instrument on the identity, and then by equivalating with this trace here, you get this equality. So far, so good. Now we can define sequential measurements. So let's say you have two POMs, E and F, which are implemented by instruments IE, IF, respectively. And then if you apply these instruments in sequence with the instrument for E acting first and the instrument for F acting second, you define an instrument of a sequential observable M with outcomes X, Y, which are ordered. And then the effects N can be evaluated as before as the pre-dual of the first instrument acting on the effect of the second observable. So this nicely illustrates how in the quantum regime, an initial measurement disturbs the measurement of the second observable. So when you take marginals, so if you trace out, for example, all the outcomes X, you don't get back the observable F anymore, but the F transformed by the quantum channel defined by the pre-dual of the first instrument, except for the case where the instruments commute, where you could say you have non-contextuality. And this will be made significant later on. Okay, so now we go to the special class of sharp observables, or projective measurements, if you like. Now, a sharp observable is a POM whose effects are the spectral projections of a self-adjoint operator O, where here lambda x are all distinct eigenvalues of O, and we denote by POX as the x spectral projection of the observable O. And I should stress that in general, these are not projections on eigenstates, but can have higher rank, as in the observable O can be degenerate, which will be crucial later on. Now, the measurement of the sharp observable O is said to be ideal if it is implemented by a Ludus instrument, which is the instrument where you sandwich the state rho by the spectral projections themselves. This is ideal because, in a sense, it is the least disturbing instrument you can implement to measure the observable that you wish to measure. And also, when you sum over all the measurement outcomes, you get a decoherence channel, which is a completely positive trace preserving band, which we just denote by DO. Right, now, there is another description of measurements, which we're not going to explicitly delve into here, but that is the description of measurement schemes, where you implement an instrument by a physical interaction with a measurement apparatus, usually unitary, followed by a measurement of a pointer observable on the apparatus. Now, a central result from the quantum theory of measurements is the following. If the unitary interaction between system and apparatus is energy conserving, as in it commutes with the additive Hamiltonian of system Hamiltonian plus apparatus Hamiltonian, then you can only implement a Ludus instrument of a sharp observable O if this observable commutes with the Hamiltonian of the system. Now, this was initially an observation made by Wigner, which was later on formalized into a theorem by Araki and Yanase, which is this paper here from 1960. But to those who are interested in learning more about this subject, I would advise reading the very recent paper on Archive, which came out just a few weeks ago, which gives a very nice overview of the topic and its developments over the years and relation to the framework of quantum reference frames. Okay, so now with all the preliminaries out of the way, we can discuss the thermodynamics of an ideal projective measurement. So if we wish to quantify the entropy production, work, and quantum heat associated with the ideal projective measurement of an observable O, given a system with an arbitrary initial state rho and Hamiltonian H0. Now, the analysis of the entropy production is straightforward, and as we will see, but the main conceptual difficulty is in disambiguating work from heat, because well, if you just look at the change in energy as you projectively measure the observable, how do you disambiguate the heat contribution from the work contribution? Now, to this end, we will use the Wigner-Araki-Yanase theorem to our advantage and introduce the following measurement scheme, which is a sequence of three operations. So first, you quench the Hamiltonian from its initial H0 to a Hamiltonian H such that it commutes with the observable that you want to measure. And for simplicity, we're going to assume that this quench is infinitely fast, so we don't have to worry about the induced unitary dynamics. And then secondly, then you implement the Ludus instrument of the observable O by an energy-conserving interaction with the apparatus, which is allowed by the Wigner-Araki-Yanase theorem. And finally, you quench the Hamiltonian back into its initial configuration. Now, should be apparent that steps 1 and 3 do not result in any change in entropy, and therefore all the energetic change can be identified as work. So therefore, if there is any such thing as heat or entropy production, comes purely due to step 2. Now, since we are implementing the measurements by a unitary energy-conserving interaction with the apparatus, it is safe to assume that there is no work associated with this process. But if there is a flow of energy into the system, it is compensated by an equal amount of flow of energy out of the apparatus due to energy conservation. So in full analogy with classical heat flow from the thermal environment, given a conservative coupling, we shall refer to such energy flow as quantum heat. Right. So now to evaluate the statistics of these quantities, we shall resort to the traditional approach of the eigenstate trajectories of stochastic quantum thermodynamics. So let's get some notation out of the way. So let's assume the initial state rho and rho prime, which is given by the decoherence channel of the observable O acting on rho, be potentially degenerate. And we shall write them as follows. So rho equals the sum over n qm dm divided by dn by p rho n. Now, P rho n are the spectral projections of rho with eigenvalue labeled by n, where the eigenvalue is qm by dm. Now, qm are all distinct positive numbers which sum to 1, and dm is the rank of the projection operator P. And the same thing for the final state. Now, to understand the second term, we note that we define by psi and phi as the eigen-decompositions of rho and rho prime, where p psi mu m is basically just the projection on the eigenvector psi mu m. Now, so if you recall, I said that trajectories are really outcomes of sequential measurements. So what we do is we augment the Ludus instrument of the observable we actually measure into a sequential measurement where we, before and after the application of LO, we apply a Ludus instrument defined by the eigen-decomposition of the initial state, psi, and the final state, phi. And it should be quite trivial to see that when you sum over all the measurement outcomes, you do not change the dynamics as relating to when you only perform the measurement of O, because the decoherence channels have a nice property that if the state rho commutes with the observable that you're decohering with respect to, it leaves the state rho invariant. So here, d psi rho gives you rho, do on rho gives you do of rho prime, but because phi is the eigen-decomposition of rho prime, then it doesn't change the states again. So you have this nice non-invasive augmentation of the measurement process. So therefore, the outcome of this sequential measurement, gamma, mu m x nu n, is the eigenstate trajectory of the measurement process for the observable O, which is associated with the sequential POM n, which we won't write down explicitly for now, but just note that it exists. So therefore, we evaluate the probability of the trajectories via Born's rule, which is given the initial state rho, the probability of the sequential measurement outcomes gamma, the trajectory, is just a trace of the sequential instrument I acting on rho, which just reduces to this quantity here. And to see that, we see, well, the first instrument projects only onto an individual eigenstate of rho with probability qmdn, so that goes out. And because the observable O commutes with phi, the x dependence actually kind of disappears, and you just get the overlap between the two, the initial and final eigenstates. Now here's the crucial part. Unless the initial and final states are both non-degenerate, i.e. dm and dn prime are equal to 1 for all m and n, then there will be infinitely many valid eigen-decompositions psi and phi for the initial and final states. And therefore, you will have infinitely many valid sets of trajectories gamma. And we will see the consequence of this when we evaluate the moments of work and heat. Now, let's first go to the evaluation of entropy production. And for this, we will need the notion of time reversal. So for here we follow the approach by Crookes in the paper in 2008, where any instrument I, which admits an invariant state pi, meaning that when you sum over all the measurement outcomes, when you act on pi by the instruments I, you get pi again. So then you can define a dual reverse instrument, I tilde, which is as follows. So first you sandwich the state rho by the pi to the minus half. Then you act by the pre-dual of I, defined by the trace, and then you sandwich by the square root of pi. And this has the property that when you start from equilibrium, as in the state pi, and you look at a sequence of outcomes x1 to xn of your normal instrument, that probability is equivalent to the probability of observing the reversed sequence of outcomes xn to x1 given by the dual reverse instruments. And therefore, the disparity between these probabilities can, in some sense, quantify the irreversibility of the measurement dynamics from which we can define entropy production. Now, what are the dual reverse instruments for our sequential measurements? So basically what we do is we look at the dual reverse of each Luther's instrument and then apply them in reverse order. But since a Luther's instrument is self-dual, as in LO star is LO, and since it admits the complete mixture, identity over D, as an invariant state, then the dual reverse of the Luther's instrument is itself. So we call it self-dual reverse. So therefore, the time reversed measurement process is given by the sequential measurement, where you apply the Luther's instruments in reverse order, which is just the pre-dual of your sequential measurement for the forward measurement process. And this has the outcomes, which are the time reversed sequence of the forward trajectories. And in order to evaluate the probability of the backward trajectories, we again use the Born rule, given the dual reversed POM M tilde, given the final state of the measurement process, as in rho prime, because we perform a measurement forward in time, some of the measurement outcomes we get rho prime, and then given that as an initial state, we perform the time reversed measurement process. And this, again, just gives us the probability of the system being in state phi mu n rather, with the overlap with the eigenstate psi mu n. And then the non-adiabatic entropy production can be defined as the logarithm of the ratio of these probabilities. And since they are both proportional to the same inner product, that vanishes, and you just get the increase in information entropy between the initial and final eigenstates. And then with a simple few lines of calculations, you can see that every moment of the entropy production reduces to the moment of the relative entropy, as in trace of rho with the kth power of log rho minus log rho prime. So namely, the average entropy production is simply the relative entropy between the initial and final states, and the variance of entropy production is the relative entropy variance between the initial and final state. Now, I should stress that the moments of entropy production are determined purely by the states rho and rho prime, and therefore are independent of the particular eigen-decomposition we chose to construct our trajectories. So far so good, no ambiguity here. So now we go to work and quantum heat. Now, with the key assumption that the energy of a general pure state psi is the expected value of the Hamiltonian on that pure state, we can define the stochastic work and quantum heat as follows. So the heat is merely the increase in expected energy as you go from the initial eigenstate psi to eigenstate phi, given the Hamiltonian we have during the measurement process, which is h. And for the increase in internal energy, you have again the same trace function, but now with the initial and final Hamiltonian h0. And by the first law of thermodynamics, you can then define the work as the difference between these two quantities, which is just given by this trace function here with the so-called work observable, which is the difference between these two Hamiltonians. Now let's go back to this key assumption we have made. Now, to those of you who are familiar with things like the two-point measurement scheme for evaluating work for a unitary process, this assumption should be raising some alarms. Because, okay, so what do we mean by energy and therefore energy change? Now, usually we say energy is a sharp property, as in it is the eigenvalue of the Hamiltonian. So you can really only talk about change in energy as you go from one pure state to another if they are both eigenstates of the Hamiltonian. And that's why, so for example, in the two-point measurement protocol, you try to resolve this by first projectively measuring the system with respect to energy and then looking at the statistics of energy eigenvalue differences. Now, this approach, sadly, cannot be used here because it will lead to a circular argument, because we want to find out how the energy of the system changes due to energy projective measurements that commute with the Hamiltonian. So using projective energy measurements to define the change in energy given projective measurements doesn't work. But for now, we will work with this assumption. But later on, when we go into the coarse-grained trajectory framework, we shall see that this assumption has an operational meaning in the framework of weak measurements. But that will be made explicit later on. Okay, so let's compute the first moments of work and heat. So the average quantum heat always vanishes, and the average work is simply the increase in expected values of the initial Hamiltonian given the initial and final state. So as with the entropy production moments, this is purely determined by the quantum states rho and rho prime, and therefore is independent of the trajectories. So far, so good. But what about the higher moments? Now, with simple calculations, we can see that the higher moments take this somewhat more complicated form, where here you have the kth moment, essentially, of the observable h minus the decoherent observable h given the eigenbasis of the initial state. And similarly here, but now we also decohere the work observable by the eigenbasis of the final state, which isn't needed here because phi commutes with the Hamiltonian, so that decoherence channel can be removed. And maybe it'll be illustrative to see how you can recover the first moments by setting k equal to 1. Now, because the decoherence channel is self-dual, when k equals to 1, then we can basically take this decoherence channel from acting on the Hamiltonian to acting on the state. And since psi is the eigenstate of rho, it leaves rho invariant, so you recover this trace here, and similarly for the work. But if either the initial state rho or the final state rho prime are degenerate, then the higher moments will only be uniquely defined in the commutative limit, whereby rho, rho prime, h0, and h all commute with each other. And it is trivial to see that in such a case, all moments of work, heat, and entropy production vanish. So it's a trivial scenario. And the reason why you get non-unique definitions of higher moments is that when you take products of these objects here, then you cannot use take these channels and then take them on acting on rho anymore. So you'll have some interference phenomena, if you like, depending on the eigen-decomposition you chose. So to resolve this issue, we shall coarse-grain our trajectories. So what do we mean by this? So if you recall, our eigenstate trajectories were built on projectively measuring the system at the beginning and at the end with respect to the eigen-decomposition of the initial and final states. But when a quantum state is degenerate, perhaps the eigen-decomposition isn't a physically meaningful thing, and we should only restrict ourselves to distinguishing the degenerate subspaces of the quantum states. So therefore, we define the coarse-grained trajectories, capital gamma, as the sequence mxn, which is, in some sense, the union of the eigenstate trajectories which share the same m, n, and x, but with the different values mu and mu. And as before, this is an outcome of a sequential measurement whereby we replace the Ludus instruments determined by the eigen-decomposition psi and phi with the degenerate Ludus instruments defined by the observables rho and rho prime, which, as before, does not change the measurement dynamics because, again, you have this property here. And again, similarly as before, we can evaluate the probabilities of the forward and backward trajectories here, where now instead of getting simple inner products between eigenstates, we have trace of the instruments acting on the identity. And the reason for this is because we have Ludus instruments acting first in both the forward and reverse trajectories. So basically, if you project the state rho with respect to just one of its non-degenerate subspaces, then the probability of that subspace comes outside of the trace, and you can just replace rho with the identity. Similarly for the backward trajectories. And again, as you recall, these are just products of the eigenvalues of the initial and final states multiplied by some trace function. So when you take the log ratio of these things, you get back the same definition of entropy reduction for any of the eigenstate trajectories which are contained in your coarse-grained trajectories. And with similar calculations, which I won't go into here, you can see that all the moments of entropy reduction for the coarse-grained trajectories also reduce to those obtained by the eigenstate trajectories. So it is consistent on the level of entropy reduction. So now we go to work and heat, and this is where we have to explicitly make use of generalized weak values. So we can quantify the conditional change of energy of a system with a Hamiltonian H and an initial state ρ, conditioned on observing outcome X of an observable M induced by instrument IM as follows. This was introduced by Alessandro Romito and myself last year. And we came to this definition by imposing three conditions on such a quantity. And these are as follows. First, when you average the conditional energy change over the probability distribution of the measurement outcomes of the observable M, you should recover just the difference in Hamiltonian expectation values given the final state and initial state. And you can see that this is satisfied because this is the probability of observing outcome X. So when you multiply by the probability, the denominator vanishes. And then when you sum over X, you just get a quantum channel, which is completely positive trace preserving. So this takes ρ to ρ prime. And here it just basically goes to the identity, right? Because it preserves its trace. So you just get trace H ρ. The second condition we imposed, which is perhaps less easy to see here, is that we want the conditional change in energy to be independent on how the state ρ is prepared. Which is to say, consider ρ as a convex combination of some states ρk. And then we want the weighted average of the conditional energy change given the states ρk to recover the conditional energy change given the state ρ. And this is satisfied by this definition. And the final condition is that when the instrument of the observable M commutes with the Ludus instrument of the Hamiltonian, we want this quantity to vanish for all measurement outcomes. And the reason for this is that when the two instruments commute, we basically are in a non-contextual setting where the order of measurements do not matter. And then this conditional energy change reduces to conditional expectation values in classical probability theory, because we have a well-defined joint probability distribution over the outcomes X of the observable M and the energy eigenvalues of the Hamiltonian H. So a conditional probability is well defined, and both the initial conditional energy and the final conditional energy will be the same if you have the same Hamiltonian. So it vanishes. So if we go back to the case of the two-point measurement protocol, for example, we see that when you only care about how the energy of a system changes conditioned on the outcomes of a projective energy measurement, the energy doesn't change if you accept this framework. Now, okay, so far so good. At least this quantity makes sense in terms of the criteria to be imposed on it, but does it make operational sense in the sense that can you actually realize such a thing in the lab? And the answer is yes, in the appropriate limits of generalized weak values, which was made mathematically rigorous by this paper here, where so this quantity here, you can explicitly see, is the generalized weak value of the Hamiltonian H on the state ρ post-selected by outcome X of the observable M. Now, while the final energy is not explicitly defined as a weak value, you can still define it as such in such terms, in the sense that this is also a weak value, but no longer post-selected by any measurements performed subsequently. Okay, so now we can apply this formalism to quantify the energy change in both heat and work variety for our eigenstate trajectories by simply replacing these instruments for our coarse-grained sequential instruments for our trajectories. And for work and heat, we recover these expressions here. And as you see, this doesn't quite look the same as this quantity here. And that's because the sequential measurement, again, has as the first component a Luther's measurement, which commutes with with respect to the degenerate subspaces of rho. So again, when this instrument acts on rho, you just take the probability of rho being in the degenerate subspace with eigenvalue qm by dm, that goes on the outside, and you replace rho by identity, and you do the same thing with the denominator. So you just get instruments acting on the identity. And so here, since you have the instruments acting on the identity, you can take the pre-joule of the instrument acting on the Hamiltonian, whereas here you just have the instrument acting on the Hamiltonian itself. And yeah, so here is the heat for the coarse-grained trajectory, and here is the work. And these quantities are uniquely defined only by knowledge of the quantum state rho, not as eigen-decomposition, and by the Luther's instrument of the observable we want to measure. And through some simple lines of calculation, you can see that when the quantum state rho and rho prime are non-degenerate, then this definition reduces back to the definition we used for the eigenstate trajectory approach. And also in the commutative limit, as in when all observables commute, so since Luther's instruments of commuting observables also commute, then the pre-joule of your sequential instrument equals itself, and heat and work vanish for all outcomes. Now, let's look at the first and second moments of work and heat. So the first moments of both work and heat agree with the eigenstate trajectory approach, namely the average coarse-grained work vanishes while the average coarse-grained work is, again, just the increase in expected values of the Hamiltonian H0 given the initial and final states rho and rho prime. Now, for higher moments, in general, you basically have to have the binomial expansion of powers of the difference of the trace functions, and it can be quite cumbersome to deal with, although it is still well defined. However, under some fairly reasonable assumptions, at least for the second moments, we can obtain simple inequalities. And the condition is as follows. So if the Luther's instruments of the final state rho prime acting after the Luther's instrument of the observable O for the sharp observables Y, H, and delta H is just proportional to the same sequential instrument acting on the identity, as in it's just equal to this thing multiplied by some number, then we can obtain these inequalities, which you can see are structurally similar as the second moments of eigenstates work in heat, except instead of the decoherence channels defined by the eigenstates psi and phi, now they are defined with respect to the states rho prime and rho. And so this condition is valid at least under these assumptions. So it's valid for the quantum heat if the observable you measure is equivalent to the Hamiltonian, which is to say that the projection effect operators of O are the spectral projections of your Hamiltonian H. And it is satisfied for both work and for heat if either the observable you measure is non-degenerate or the final state rho prime is non-degenerate. Of course, this condition is not going to be satisfied in all cases, but when it does, we know that we have this inequality. Now, for the quantum heat, we can use Lieb's concavity theorem to show that whenever this inequality holds for the second moments of coarse-grained quantum heat, then the variance of the coarse-grained quantum heat is never any larger than the variance of the eigenstate quantum heat for any possible set of eigenstate trajectories. However, such a relationship will not be guaranteed even when this inequality holds for the coarse-grained fluctuations in work. And this is going to be model dependent, and in fact, you can see, as we will see in the next slide, you can even have the opposite relation hold between them. So let's just look at this with a very simple example, simplest one I could think of, where the system is composed of two qubits. And you have the initial state of the qubit as the thermal state of the initial Hamiltonian, and you choose the Hamiltonian such that the state rho has only a single two-dimensional degenerate subspace. Then you quench the Hamiltonian to a non-degenerate, non-commuting Hamiltonian H, and then you projectively measure an observable O equals H. And therefore, you already have all the conditions required to obtain the inequalities for the second moments in the previous slides. But also, for simplicity, we choose parameters to ensure that the final state rho prime is also non-degenerate. Therefore, every possible set of eigenstate trajectory gamma can be parameterized by the degeneracy of the initial state rho, which is simply the block sphere angles theta and phi for the single two-dimensional degenerate subspace. This allows us to basically have a plot, essentially. So panel A, so here the x and y axes are the degeneracy parameters theta and phi. So every point on the surface corresponds to a particular eigen-decomposition of the initial state, resulting in a particular eigenstate trajectory for the measurement process. And on the y-axis, we have the excess in the eigenstate fluctuations in quantum heat in relation to that of the coarse-grained trajectories. And we see that, as predicted, this is always positive. Now, in panel B, we have the same thing for the fluctuations in work, except now we have the opposite relation. We have the excess in coarse-grained fluctuations of work in relation to that of eigenstates fluctuations of work. And we see that in this instance, this is always positive. But if you change just the eigenvalues of the Hamiltonians you've chosen in the protocol, then this relationship can flip, and it can also mimic that of the eigenstate trajectory approach. So there's that. I don't particularly have any intuition for this. It just happens to be the case for this model. Right, so let's conclude. So as we demonstrated, the eigenstate trajectory approach of stochastic quantum thermodynamics fails to give unique higher moments of work and heat when the quantum state being measured has degeneracies. However, by coarse-graining the trajectories and generalizing the definition of stochastic energy change as the change in the expected value of energy conditioned on measurement outcomes, we can resolve this problem. And at least for the case of ideal projective measurements, this constitutes a true generalization, which is to say that the coarse-grained trajectory approach reduces to the eigenstate trajectory approach when the latter does not result in any ambiguities, but it provides unique and well-defined alternatives when it fails to do so. Thank you.
Thanks very much, Hamid. So let me just bring back my video. So yeah, I'm afraid I apologize everyone for these very annoying symbols at the bottom of the screen, which I have no idea why they don't disappear automatically. Luckily, they didn't really get in the way of your slides, so everything was clear.
That's great.
But I think we're going to have to find an alternative to Skype from now on, because as much as I find non-determinism interesting, this particular kind of non-deterministic behavior is quite annoying. Okay, so as always, yeah, we have plenty of time for questions. So lots of people are already clapping and saying thanks for a nice talk. But yeah, just remind everyone, you can just write your questions in the YouTube chat window. So of course, there's always a bit of a delay. So maybe I can just start off by, so I was just wondering, let's say operationally, I actually want to try and measure these trajectories. What does your formalism tell me that I have to do? From an operational point of view,
right. Okay. Shall I continue the screen sharing so I can?
Yeah, if you go back to screen sharing, yeah, that would be good.
Yeah. Okay. Sure. Start sharing. Okay, so let's go to the right. Okay, so essentially what you do is operationally you have to have three pointer systems which you use for the weak measurements. So at first you weakly couple the Hamiltonian H0 to apparatus 1, with the strength of the interaction vanishing to 0. Then you quench the Hamiltonian from H0 to H, and then you again weakly couple the Hamiltonian H to your second apparatus. Then you implement your sequential instruments, again via whatever measurement scheme allows you to achieve this. And then you weakly couple the Hamiltonian H to a third apparatus 3. Then you quench the Hamiltonian back to H0, and then you weakly couple that to a fourth apparatus 4. And then for each sequence of measurement outcomes you observe, you look at the difference between on the pointer observables for the pointer systems of apparatus 4 and 1 to look at the increase in internal energy conditioned on the measurement outcome. And then you look at the difference between apparatuses 3 and 2 for the quantum heat. Then you subtract and you get the work. I mean, it's operationally definable, but whether you can do it in the lab, I will remain silent on this because I'm pretty sure it's impossible.
So you need basically four different kinds of detectors.
Yeah, you need 4 detectors which are in the limit of vanishing interaction strength, and you also need to implement ideal Ludus instruments for your sequential observable. And this is state dependent, so you also need to have perfect state tomography of your initial and final states. So it's an involved process, but alternatively, you could say, well, okay, as long as the weak measurement process is done, then you can say, well, the trajectories you are simulating are not for the process which leaves the ideal measurement of the observable O non-disturbed, but you're measuring some other process, which is given by non-ideal disturbing instruments. So in that sense, what you're doing is not so much simulating the thermodynamic properties of the ideal instrument, but of the observable O, but rather of a disturbed, noisy instrument, if you like.
Okay.
Yeah, if that makes sense.
Yeah, thanks. Yeah. Okay, don't be shy, guys. Feel free to ask any questions you have. So maybe I can ask you about the example. I mean, what?
Yep.
I mean, what actually was the Hamiltonian there? I mean,
well, okay. It's in the paper. You can look at it. It's basically a Hamiltonian which couples with so it has equal spacings, and the spectral projections of the Hamiltonians are basically so the degenerate subspace for Hamiltonian H0 is essentially identity on qubit 1 or qubit 2 rather, tensor projection on say one of the say 0 for example on the other qubit. So that gives you a 2-dimensional subspace, and the other ones are the other products of projections, which just gives it to you. So maybe I can.
So are they?
Maybe I should say. Yeah. Maybe I could just get the paper up.
Yeah.
I don't know. Yeah. Let's see. I'll stop share screen for now.
Right.
Yeah. Sorry.
No problem.
I probably should have written this down.
I was just wondering because I mean it wasn't really clear to me what these block angles. I mean how they parameterize the setup. So I mean, is it like 2 identical qubits then, or I mean, because I can
exactly
see,
yeah
right.
Well, it's 2 qubits, but yeah, I'll just get the paper up and then it'll become self-apparent.
Okay.
Hopefully. Okay. So now we can share screen again. Okay. Yeah. Yeah. So it's something like this. So this is the Hamiltonian H0. Let me just zoom in further. So here you have a projection on an orthonormal basis. So you have plus and minus. So you project on the eigenstate plus tensor identity on the other qubit. And then you have projections on minus, plus, minus, minus for the other terms. So basically, this thing is degenerate, right? Because the identity can be decomposed into arbitrary orthonormal bases of that state, which are given here, right? And therefore, that's where the block angles come. Yeah, theta and phi, if that makes sense.
I see. So this is just an arbitrary state of the second.
Exactly. Yeah, yeah. I mean, the key is that because the state is degenerate, at least in the the subspace projected onto by this operator, you can have infinitely many eigen-decompositions of that state, which you can parameterize by theta phi.
I see.
Yeah, and that's why we can make plots essentially.
Right, right. So I mean, but if you just considered even just to, like, I would say maybe a simpler case of two identical qubits, I mean, with the same splitting, then you have a degeneracy. I mean, the 1, 0 and 0, 1 states are then degenerate, right? I mean, I sort of thought that's where you were going with that, but that Hamiltonian actually seems to have rather a unusual interaction term, right? I mean,
I mean, I guess I don't know why I chose this one, but then basically, so we can see that then you can have the observable we measure is again defined this way, where now 0 and 1 are defined by these rotated angles, right? So it doesn't commute with the Hamiltonian. I just thought it was a nice way of, looking at non-commutativity and you get quantities and what have you. Yeah, I mean, there's multiple ways of doing examples.
Of course, no. I was just sometimes you learn something by finding out why a specific example was chosen, but I mean,
there was no reason. It just seemed easy to calculate. So.
Sure, fair enough. Yeah. All right, so we have a question from Karen Hofhannisyan. So hi, Karen. So Karen says, when you reconstruct the actual statistics from the higher moments, you obtain a quasi-probability for general initial states, right? I mean, for work, for example.
Right. Okay. So so basically, this approach of how I defined like conditional energy changes, at least for the average moments, so the average energy change is equivalent to the quasi-probability distribution for the single measurement protocol by Al-Badrian. However, I'm not sure about higher moments. I didn't look into that. But the key point is that instead of looking at using weak values to define quasi-probability distributions of definite energy changes, we maintain well-defined probability distributions as given by the Born rule. So the probabilities are well-defined, but now the conditional energies are now weak values. So in general, like at least in this case, for general instruments, these weak energies can lie outside of the range of the spectrum of the Hamiltonian. However, I discussed this with someone else recently as well. For the case of trajectories, you actually get them all these energies to fall within the spectrum of the Hamiltonian. Why? Because so let's just look at this term here, or rather this term, for example. It's easy. So so this is the trace of the instrument Im acting on the identity multiplied by h, divided by the trace of the instrument I acting on the identity. So then you can basically divide identities by the dimension of the system. So essentially you have the expected value of the Hamiltonian given the normalized state you obtain when you measure the complete mixture by your instrument. And then similarly for the other term, except now it's the normalized state you obtain when you measure the complete mixture by the pre-joule of your instrument. And these are, at least for projective measurements or sequences of projective measurements, these will be states with trace 1. So you actually get a nice property that the conditional energies all fall within the spectrum of the Hamiltonian as well. But I mean, it is possible that this approach is equivalent to having quasi-probability distributions. I just haven't looked at that in any detail myself. It remains as an open question.
Okay, thanks very much. So we have another question from Andre Timpanaro, who says, I got a bit confused at one point. Does the coarse-grained trajectories recover the full statistics of the usual eigenstate trajectory approach when there are no degeneracies, or just the first moments?
Okay. Well, the thing is, when there are no degeneracies, then there is nothing to coarse-grained. So basically, your observables. So let's see where. So these things just reduce to the Lewis instruments of the eigen-decompositions psi and phi. It's just that now you have a unique eigen-decomposition psi and phi because the states are non-degenerate. It's just that this framework allows you to see, like, generalize the eigenstate trajectory approach to the coarse-grained trajectory approach. So to repeat myself, when there are no degeneracies, the two approaches are equivalent because there is nothing to coarse-grain. But when there are degeneracies, then the coarse-grained trajectory approach coincides with the eigenstate trajectory approach only in the instances when the eigenstate trajectory approach does not result in ambiguities, which is to say all moments of entropy production, the first moments of work and heat, and all moments of work and heat when you are in the commutative limit, where it's trivial and all moments just vanish to zero.
Okay. Thanks very
I
much.
hope that answers the question.
Yeah, I think hopefully, but let's see if Andre writes anything back. Okay, so I mean, unless there are any further questions, I think I got all of them. So I'd say that's probably a good moment to conclude. So yeah, so thanks very much everyone once again for tuning in. I apologize again for technical issues. I'll be finding an alternative to Skype, so hopefully this won't happen again. But especially thank you so much, Dr. Hamid Mohammady, for a really nice talk.
Thank you.